All right, so for 4, we're going to talk about the fundamental theorem of calculus. So I'm just going to add 2 properties above because they definitely might be helpful at some point. But if we're now going to be evaluating integrals too. So instead of just having the plus c on our integrals, we're now going to be evaluating them. So if you have the integral and you're finding that the lower and the upper number are the same thing, no matter what, your integral is going to be equal to 0 when you evaluate. If when you look at your integral, you're like, well, my parameters are written sort of in the wrong order, dx, what you can do is pull out a negative, which will flip the parameters that you have to work with. So your answer would just have an opposite sign in front of it. So if it was positive, then it would become negative. If it was negative, it would become positive. So again, what we're going to be doing is we're going to be evaluating the integral. So in the past, all we did was integrate. So if we saw x squared minus 3, we would say x to the third over 3 minus 3x, and we'd put a plus c on it, and we'd be done. But now, because there's numbers on the integral, this is a definite integral, we're going to be evaluating from 1 to 2. And the way that you evaluate is you take the top number, 2, and you sub it in everywhere you see an x, minus, so it's top minus bottom. And then we're going to do the same thing with the 1. And we're going to simplify. We're going to try not to use any calculators. So we get 8/3 minus 6 minus 1/3 plus 3 when we distribute the negative. So we get negative 9/3 minus 6 plus 3. Sorry, that's not 9/3, that's 7/3. Eraser. 7/3. And then if we get common denominators here, if I make these guys all 3, that gets me 9, that gets me negative 18. And I end up with a negative 2/3 final answer for that. Okay, so again, you integrate first, then you evaluate by subbing in the top number and taking away when you do it with the bottom number. All right, so if we look here, this is 3x to the 1/2. So if I integrate, I get 3x to the 3/2 over 3/2. Remember, this 2 is going to come up, and I'm evaluating from 1 to 4. So I would recommend simplifying first. So if that 2 comes up, I then get 6x to the 3/2 over 3, which can still be reduced. So I have 2x to the 3/2, and I'm evaluating that from 1 to 4. So top number goes in first, and then number 1 goes in. So 1 is nice and easy. That doesn't do much. But if you see 4 to the 3/2, that's the same thing as saying the square root of 4 to the 3rd power. Okay, so the square root of 4 is 2, 2 to the 3rd is 8, and 8 times 2 gets me 16. So it's 16 minus 2, which gets me a final answer of 14 for that one. We don't need common denominators there. All right, in terms of trig here, we have the integral of secant squared. Well, that's tangent. And I'm evaluating from 0 to pi over 4. So I'm taking the tangent of pi over 4, and then I'm subtracting the tangent of 0. Well, the tangent of pi over 4 is 1. Remember the coordinates, radical 2 over 2, radical 2 over 2, and these guys would be 1, 0. And the tangent of 0 is 0. So that gives me a final answer of 1. Now what happens, we've never really seen an absolute value function so far. So there is a couple extra things that come into play here. So when you see an absolute value function, first thing I would do is set the value inside equal to 0, and you get 1/2. Okay, so that means it's going to cross at 1/2. Now if we plug some other points in, we're only going from 0 to 2. Say we plug 0 in, well 0 is going to get us a positive 1. If we plug 1 in, 1 is going to get us a 1. And 2 would get us, 2 goes in, we get 4, 4 minus 1 gets us 3. So this is what this function looks like. And ultimately, what integration is, it's finding the area under the graph itself. And we have 2 regions here. So this is why we can't necessarily just integrate it normally. So this is where you're going to be creating a piecewise function. So we have the absolute value of 2x minus 1. We have one part of the graph that's coming down on the left-hand side, and we have one part that's increasing. So the negative portion of this graph goes parameter-wise from 0 to 1/2, and the positive version of this graph goes from 1/2 to 2. So there's my two pieces. So what I'm going to do is I'm now going to take my original function, and now I'm going to split it up into two different integrals. One is going to go from 0 to 1/2, and that's the negative. And then the other one is going to go from 1/2 to 2, and that's the positive. And then I can integrate each one. So if I come over here and do that, I get negative 2x squared over 2 plus x, and I'm going from 0 to 1/2, plus 2x squared over 2 minus x, and I'm going from 1/2 to 2. Those 2's are going to cancel. So now when I sub in my numbers, I get negative 1/4 plus 1/2, and then minus 0, because 0 is nice and easy. Plus, now I sub 2 in, I get 4 minus 2 minus 1/4 minus 1/2. So negative 1/4 plus 1/2 is 1/4 plus 2, and this guy gets me negative 1/4, or 1/4, sorry, so that's positive 1/4 plus 1/4. A fourth and a fourth make a half, so this is 2 1/2, or 5/2 for our final answer for that one. All right, two more on the back. So again, integration is area. So when you see things worded as find the area, it means the exact same thing. So you want to set yourself up an integral. You have your equation to work with, and it's saying you're going from the x-axis and the vertical lines x equals 0, x equals 2. So we want to stick with the x's. So 0 to 2, and then we have dx. So we're going to integrate. So we get 2x to the third over 3 minus 3x squared over 2 plus 2x, and we're going from 0 to 2. So I plug 2 in everywhere. And then 0 is just going to get me 0, so I'm just going to write 0 for that. So I get 16/3 minus 12/2 plus 4. This is 6, so it's basically 16/3 minus 2. If I get a common denominator of 3, that's going to get me a final answer of 10 over 3. Now the difference here is it didn't just say evaluate, it asked for the area. So if it's asking for area, just make sure you put units squared there. And then I'll just make a little note, since asking for area. You don't have to do that otherwise, it's only if it's a word problem where they do that. All right, we had a mean value theorem way back for derivatives. Now we have a mean value theorem for integrals. And all it's going to be is this nice formula. Looks complicated, but I can assure you it's really not. So it says if f is continuous on the closed interval, so it's still got to be continuous, there exists a number c in the closed interval such that that boxed formula is true. So first thing we're going to do, here's our a and our b. So 1 over b minus a integral from a to b of our function, 3x squared minus 2x dx. So we have a 1/3 hanging out front, and I'm going to first integrate. So I get 3x to the third over 3, 2x squared over 2, which I'm evaluating from 1 to 4. 3's cancel, the 2's cancel. So I have 4 to the third minus 4 squared minus 1 to the third minus 1 squared. Well, 4 to the third is 64. 4 squared is 16, and this guy gets me 0. 64 minus 16 gets me 48, and 48 times 1/3